All right, so in example 3, we're going to study a pendulum with an elastic wire. So this is a wire that can stretch as well. We're going to make a modification to the problem. We're going to add an external moment to it. So we're going to say that there's some external moment acting on the pendulum as well, which will be capital M of t. And we're just asked to determine the equation of motion for this system. And in this class, we only know how to use Newton's second law, so that's what we're going to do. We're going to use Newton's second law. There are other techniques out there, but we won't cover them in this class. Okay, so we'll come back down here, and I'm going to just draw that moment here as well, M of t. And then gravity is also acting on the system. The elastic wire has a spring or a stiffness of K. And we're going to measure the rotation of the pendulum with the angle theta of t. So first thing we're going to want to do is create a coordinate system. Anybody have an idea for what kind of coordinate system we should use for this problem?
Polar.
Why polar?
Because it's just rotating about a point.
Yeah, so we're going to want to use a polar coordinate system because we have rotation about a fixed point. And there's only rotation about a single fixed point, more specifically. So we're going to put a polar coordinate. Well, first we'll say that our origin is going to be at the ground. We'll put an origin at the, well, let's say the connection of the spring or the wire to the ground. Which is the point of rotation. So whenever you're using polar, you have to put an origin or put the coordinate system at the point of rotation. If you're using Cartesian, you can put your coordinate system wherever you want, or your origin wherever you want. And we say we're going to use a polar coordinate system. Polar, also known as radial and transverse. We'll go ahead and do that right now. So we'll put our E hat R vector pointing from the origin towards the particle. That's E hat R. E hat theta will be normal to that, and then there's a K vector coming, or an E hat Z, we can say, one of those two pointing out of the page. And then lastly, we'll have counterclockwise rotation be positive. That's just a standard for right-hand rule. We're then going to go and create position vectors. In this case, there's only one particle, so we only need to worry about that single particle. We'll draw a position vector from the origin to the particle. We're going to call this R, underline, underscore, R vector of t. And then we're going to want to write out our R vector. And in this case, this is going to be equal to the quantity scalar R of t, so that measures the deformation in the radial direction, plus some R0, which is the unstretched length of the wire. And all of that acting in the E hat R direction. Actually, I said we're adding a moment to this problem. I was wrong. We're adding a moment to a later problem. So you can actually ignore that. We're not going to add it here. I got way ahead of myself. On Wednesday, we'll see a problem that has a moment in it. If we wanted to, we could represent a moment here using an applied force at the particle. We won't do that here. We'll deal with a moment on Wednesday. Okay. That doesn't change anything that we've done so far. That just changes what I talked about in the beginning. Okay, we're now going to go and compute velocity and acceleration vectors. We're just going to take time derivatives of r of t. So r dot of t will be equal to first r dot E hat r. R of 0 is just a constant, so it doesn't have a time derivative. And then we have to take the derivative of E hat r, which gives us theta dot E hat theta. So we'll get r plus r0, all of that. Oop, we left out the theta dot, multiplied by theta dot and the E hat theta direction. We can then move on and compute our acceleration vector. This will be equal to r double dot minus r plus r0 theta double dot, or that's actually theta dot squared in the E hat r direction plus quantity r plus r0 multiplied by theta double dot plus 2 r dot theta dot E hat theta. So when you're applying polar coordinates and computing your acceleration vector, you have kind of two options. You can go and compute the derivatives of the unit vectors, or you can just use the formulas that we drive to class, although the scalar r will change based on the problem as well. Okay. Now that we've dealt with the acceleration, we're now ready to move on and deal with the kinetics, or the forces acting on the body, starting with a free body diagram. And what we're going to do is I'm going to stop here and I'm going to have you guys work on the free body diagram with your neighbors around you, and then I'll come walk around and answer any questions or address any comments. So pretty much everybody got the free body diagram, and some people started to decompose forces. Some people chose to decompose the spring force, others chose to decompose the gravity force. We're going to go through and we'll see what I would do, and I'll talk through it. So first we're going to draw our particle. We have a gravitational force pointing downwards. That's just mg. Then we have the spring force here. Let me fix that. The spring force is just kr. So we're obviously working in, well, these are pointing in different directions that are not, perpendicular to each other, implying that we're going to have to break one of these down into components so that they're in the same coordinate system. So you have a choice of breaking either the spring force down or the gravitational force down. And what we're going to want to do is we're going to want to go back and look at what our coordinate system is that we've chosen to analyze the problem. In this case, this is a polar coordinate system, and we're going to want to work with all of our forces in this coordinate system. And what that then tells us that if kr is in the E hat r direction, but mg is in neither the E hat r or the E hat theta individually or solely, and that tells us that we're going to have to break up this mg force into components. There was a question about what this r0 is. This r0, so the total length from the origin to the particle is equal to the unstretched length of the spring plus the stretched length of the spring. And this RT measures the stretch in the length of the spring, and that's what gives us the force due to that spring. And this R0 is the unstretched length. Now you could, if you wanted, you could say that this is big R of t, and then do the kinematics using big RT. There's nothing wrong with that. But then when it comes to the force, here you would have to write K times big R minus the unstretched length, because it's only the stretch in the spring or the change in the length that is giving us this force. So you can do either of these. It's fine. You just have to account for it in that case. We're going to stick with little r because that's what I have. That's what we started with. Okay, so we're going to break up this mg force into two components, one in the E hat r direction, one in the E hat theta direction. We already know that this angle right here is theta, and so this will be mg sine theta. This will be mg cosine theta, and we'll worry about the directions or the signs in a moment. Any questions on the free body diagram? Or how we broke up the forces? Okay. So in that case, we're going to move on, and we're now going to apply Newton's second law. We'll just say sum of the forces, vector force is equal to the mass times the acceleration vector. So for our forces here, we're going to have, in the E hat r direction, we're going to have minus kr plus mg cosine theta. Oops. All of that in the E hat r direction, minus mg sine theta E hat theta equal to the mass times our acceleration. So we'll have first r double dot minus r plus r0 theta double dot. Oh, that's theta dot squared. E hat r direction plus m times r plus r0 theta double dot plus 2r dot theta dot E hat theta. So from here, we're going to break this up into components and look at each component individually. We'll say here that E hat r, in that direction, we get minus kr plus mg cosine theta is equal to m r double dot minus m r plus r0 theta dot squared. And that's everything in the E hat r direction. In E hat theta, we end up with minus mg sine theta equal to m r plus r0 theta double dot plus m, well, let's put the 2 in front, 2 m r dot theta dot, and that is everything in our E hat theta direction. From here, we can go put this in a more standard form where we'll have mr double dot minus mr plus r0 theta dot squared plus kr minus mg cosine theta equal to 0, and then m times r plus r0 theta double dot plus 2m r dot theta dot plus mg sine theta equal to 0. All right, so we end up with 2 equations of motion, and that's because there are 2 what we call degrees of freedom, or 2 ways that this particle can move. First, the particle can move radially with r of t, or it can move angularly with theta of t. Are these equations linear or nonlinear? All right, there's 2 options. You can just take a guess. You got a 50-50 shot. Yeah. They are nonlinear. Yep. Why are they nonlinear?
because it's like a sinusoid?
So, there are several reasons why these equations are nonlinear. First of all, so anytime we have something like one of the variables squared or a derivative of it squared, that's immediately a nonlinear function because it's not linear. Linear would just be theta dot. Any kind of function or trig function acting on a variable is also nonlinear because it's not, if you plot cosine theta, it's not a straight line. That's what linear is, just a straight line. Anytime you have a multiplication of two different variables, like r dot or theta dot, or their derivatives or non-derivatives, that's also nonlinear. My second question is, are these coupled or uncoupled equations? Okay.
Is it uncoupled because of the k term?
It is not uncoupled, actually.
Is not, so it is coupled.
Yeah. So these equations are coupled, and the reason why they're coupled is because we have, and this is the equation for r, because it's got the mr double dot there. This is the equation for theta, because it's got the theta double dot in there. And it's coupled because we see theta dot here and a theta here, and here we see, well, r and an r dot here as well. So in this case, these equations are coupled due to that. So we have a nonlinear pair of coupled ordinary differential equations. We're going to go ahead and we're going to linearize these, and we won't be able to eliminate the coupling. And if you want to eliminate coupling, you've got to go to another class. You've got to go to 3530. But we'll linearize these, and we'll see what the linear equations look like, and we'll see how it's almost decoupled. So we're going to linearize by assuming small displacements. That's both translational and rotational. And we're also going to assume small velocities. And that will allow us to deal with the theta dot squared term. So what this means is that r, theta, r dot, theta dot, these are all much, much less than 1, so they're all small. We're not making any assumptions about the accelerations. Acceleration could be whatever they want to be. Those could be large, and it doesn't affect our analysis. So what this then implies is that the sine of theta is going to be approximately theta. The cosine of theta will be approximately 1. Theta dot squared, so we're squaring a very small number, so we're going to get a drastically smaller number. We're just going to be able to say that this is approximately 0, or it's so small that we can neglect it without any effect on the result. And then also r dot times theta dot, so will also be approximately 0, again because we're multiplying two very small numbers. Okay, if we do that, we're going to eliminate a bunch of terms, and we'll end up with, for the first equation, we'll end up with mr double dot plus kr is equal to mg. So we've actually eliminated the theta from that equation. Then for the second one, we'll get m times r plus r0 theta double dot plus mg theta is equal to 0. And here we're not able to eliminate the coupling. We still have this r appearing in the theta equation. But we can eliminate the mass from the second equation, and we will do that, and then we'll also end up dividing by this r plus r0. In that case, our equations of motion will be mr double dot plus kr is equal to mg. Then theta double dot plus the quantity g divided by r plus R0 times theta equal to 0. And those are our linearized equations of motion. And I want to point out that if you used a big R instead of this R plus R0, you would still be able to do this division because big R can never be 0. It's one of the constraints. You're never going to divide by 0. Now, wavered in here, little r can be 0. And then as a result, you get G divided by R0. So it's still not going to blow up and go to infinity. Okay, any questions on this?
On the second equation, why does it benefit you to divide by r plus r?
Sure, yeah. So the major benefit for that division comes in when you're trying to solve these equations. That's really the benefit here. Wait, hold on. These are still nonlinear because we got an r times a theta. Okay. This should reduce down. I believe this should reduce down to theta double dot plus G over R0 theta equals 0. However, I need to go investigate that because these are still nonlinear because we're still, in this case, we have R and theta and is multiplied by each other or divided by each other, whatever, which is still nonlinear. I need to investigate this. I'll tell you the final result on Wednesday. And we may need to enforce small accelerations as part of this in order to fully linearize this. Any other questions? Okay. Certainly if we enforce small accelerations, then r times theta double dot will be approximately 0. But I want to see if there's a way to do that without enforcing that. If we do enforce that, then we would just say that we have small motion. We wouldn't specify displacements, velocities, accelerations. We would just say small motion, period. Okay, any other questions before we move on to friction? The coupling? Yeah. So, in the original equation of motion, coupling occurs when you have mixed terms in each equation of motion. So, this is our equation of motion for r of t. This is our equation of motion for theta of t. And so coupling means that we have mixed terms, basically meaning that we have, this is our equation for r, and we have a theta here, and we have a theta here. Whereas if they were decoupled, there would not be a theta, there would not be a theta in this equation. And down here, we've got r here, we've got r dot here. If they were decoupled, we would not have r in the second equation. That's what coupling is. So what it implies is that the behavior or the response or the radial displacement is dependent on the angular displacement, and the angular displacement is also dependent on the radial displacement as well. Okay. Any final questions? Okay, in that case, we are going to move on to discuss friction here, and then we'll do another example problem. So friction is a force that just always opposes motion, meaning that it's always going to be pointing in the opposite direction that a particle is moving. We are going to generally we're going to study Coulomb's law. This is not the only law for friction out there. This is just by far the simplest law. Coulomb's law Let me switch back to red here. Coulomb's law is simply, we'll just write F with a lowercase f for subscript, so that's the force due to friction is equal to mu times the normal force. Have you guys all seen Coulomb friction before? Generally it comes up in physics. Yeah, you know, you get a box sliding on the ground or something. Okay, so Coulomb's law is mu times the normal force. Normal force, depending on the system, is generally related to the weight of the body. If there's angles or something involved, then it may not just be the weight, it may involve other things as well. But generally, always related to the weight. If you have two particles contacting each other and rubbing up against each other, you can then use Coulomb's law in terms of friction, and then you would have a different normal force, which would be based on the contact between them. We'll deal with impacts and contacts when we go through impulse momentum. Next week we're doing energy, and then the week after that we'll do impulse momentum. And then we'll do impacts right before the exam, basically. All right, so there are two types of friction. There is static and kinetic. And generally, static friction, or mu sub s, is either going to be equal to or greater than mu sub k, or the kinetic friction. And if you were to plot what this coefficient of friction is versus the force being applied to a system, you would find that it's not a linear relationship, or there's not just a bilinear relationship. You would end up finding that it really it varies with the force. However, you can just simplify and break it up into having a static friction component and a kinetic friction component. Static friction is what keeps an object stationary. You know, when you're pushing on something, if I push on this table, or this chair, static friction resists my push, and if I push hard enough, it will start to slide. And when it starts to slide, it switches from static friction to kinetic friction. Okay, and so yeah, once you overcome static friction, kinetic friction then takes over and works to slow a moving object, or resist that motion. And then typically, I know I wrote above that they could be equal, but typically mu s is just greater than mu sub k, such that it's harder to initiate motion than it is to sustain motion. Okay. Did you guys cover static and kinetic friction when you did it in physics? Okay. But sometimes they don't do that. They don't split it up, so I don't know. Okay. So does that mean you guys are all experts and can do the next example without me? I see a lot of no's, but I'm going to interpret that as a yes. And so I'm going to let you guys work on the example, and I'll come around. Okay. So like I said, I'm just going to give you guys a coordinate system, and then you can go and start the example. We're going to use Cartesian coordinates here. The pulley is massless, so we're just going to ignore its rotation. Although you will likely need to draw a free body diagram for it, but we don't have to worry about the kinetic or the kinematics of it. We're going to put our origin, we're going to put it right here where that pulley connects to the ground. We're going to have standard Cartesian I and J here. And then standard counterclockwise rotation is positive. Okay, so we defined Cartesian coordinates, this I and J vector. If you wanted, you could put this coordinate system, say like right here, and that would eliminate a J component for M1 and a J component for M2. Nevertheless, I put the coordinate system where I did, and we're going to go with that. So we're going to need two position vectors. First, an R1 here, and we need an R2 here. And I'm also going to define some extra dimensions. First, we're going to say that this vertical distance here is h. This horizontal direction here, oops, let me do that again. I'm going to say that this is just a. the vertical distance down to the mass 2, I'm going to call that Q. And then this horizontal distance, I'm going to call that B. And then the position vectors are going to be R1 of t is equal to minus a minus x, that's x of t here. That's in the I direction, plus h in the j direction. And then R2 of t will be equal to b in the I direction minus q plus y in the j direction, because y is pointing down. To compute our velocity vectors, we're just going to take the derivative of those position vectors with respect to time. We'll get here r1 dot is equal to x dot I plus 0j. R2 dot is equal to 0I minus y dot in the j. And then we can go and compute the acceleration vectors. We'll get r1 double dot is equal to x double dot, the I plus 0 in the j direction. For r2 double dot, we're going to get 0I minus y double dot j. From here, we're going to go ahead and start drawing free body diagram for this system. We're going to draw one for each object here. I'm going to draw the pulley, although the pulley is going to end up being rather simple. So you could decide to skip the pulley and that would be fine. I'm going to draw it for completeness. So first, mass 1, pulley, and here we'll have mass 2. Forces acting on mass 1, we have M1G pointing downwards. We have a tension force in the wire, we'll use capital T. Got some normal force pointing upwards, which we'll say is capital N. And then for positive displacement, which this body is going to move to the right, or this particle is going to move to the right, friction is going to then point to the left to oppose that motion. So we'll have our friction force here, FF. On the pulley, we're going to have, we'll have our tension force to the left there, and then the same tension pulling down. If the pulley had mass, then we would need to consider that. We would end up having a T1 and a T2. We would need to relate them because they would end up depending on the angular acceleration of the pulley. And we would need to do some of the moments, which we haven't covered yet. All right, so on mass 2, we have the tension pulling up, that's our tension T, and then we have the gravitational force M to G pulling down. And that accounts for all of the forces. Very strategically, I placed M2 away from the wall so that there's no normal force there, but you could easily have M2 sliding along that wall, and then you would have to account for a second friction force as well. And then you would have to ask what is the normal force, and you would probably need to have an external applied force, some force here like F of T, that is pushing that mass against the wall to incur that normal force. That's a case where the normal force would not be equivalent to the gravitational force. But we didn't have that, so we're going to leave that out. Okay, from here, we're now ready to apply Newton's second law. Again, this is the sum of the forces. It is equal to the mass times the acceleration. And we're going to do this for every object or every particle. So we're going to start with block 1. In fact, actually, we'll just do the pulley right here. For For the pulley, we're just going to find the tension equals the tension. So this is why I said you can just skip the pulley. There's really nothing there to add. Unless we had like a moment applied to it or it had some inertia, then we would actually have to apply Newton's second law to it. All right, so we'll just do block 1 here. We're going to have minus FF plus the tension in the I direction plus N minus M1G in the J direction is equal to M1 X double dot in the I direction plus 0J. So we're going to end up finding that for the I direction, we will get M1 X double dot plus FF is equal to the tension. We can write this as M1 X double dot plus mu. I'm just going to put here KS times the normal force equal to tension, and we'll come and fill in what that normal force is in a moment. In the J direction, we get N minus M1 G equals 0, such that the normal force is equal to M1 G. And then if we come back up here, we get M1 X double dot plus mu KS M1 G is equal to the tension. For block 2, we're going to have, let me scroll back up here, we will have just forces only in the vertical direction, so 0I plus T minus M2G in the J direction is equal to M2 times 0I minus Y double dot J. And again, we don't need to worry about any forces in the I direction, simply because there aren't any. So what we'll end up here with is T minus M2G is equal to minus M2Y double dot. Such that we'll end up with the tension T is equal to M2 times G minus Y double dot. And then from there, we can plug in for the tension in our equation of motion for X double dot, or for X, and we'll get M1 X double dot plus mu KS M1 G equal to M2 G minus Y double dot. We'll leave it as that for now. Okay, any questions on this analysis so far? Okay, then we're going to continue on. So we are asked, let me scroll back up real quick. So we're asked to determine the maximum mass M2 such that the system remains at rest. When the system is at rest, that means while the position is not changing in time, and that implies that the accelerations as well as the velocities, but we don't need the velocities, all of those are equal to 0. Yeah, so this is our static equilibrium. Going from the equation right above here, we'll lose the x double dot, we'll lose the y double dot, and then we'll find that, in this case, this is mu s m1 g must be equal to m2g. So conveniently, we can eliminate gravity from this. So gravity doesn't play a role in this. It all has to do with the masses. And honestly, at this point, we'll find here that M2 must be less than or equal to mu S times m1. That is our answer, and if you go in and you plug in all the numerical values, you'll find here that m2 must be less than or equal to 0.6 kilograms. All right. Any questions? Okay, we'll then move on to part B. This is where the bodies are in motion, meaning that the accelerations and the velocities are non-zero. We also still don't care about the velocities because they're not in our equation, but the accelerations are non-zero. So we'll just say x double dot not equal to 0, y double dot not equal to 0. And of course x double, well, we'll get to that in a moment. All right, so we have m1 x double dot plus mu k in this case because they're in motion. m1 g is equal to m2 times g minus y double dot. How many unknowns are in this equation? See 2. Everybody agree there are 2 unknowns? What are the unknowns? Or you gotta say that louder.
X double dot, y double dot.
How many equations do we have? Can we solve this? So we have 1 equation, 2 unknowns, so no, we cannot solve this. Is there something that we are missing? Well, we need another equation. Where can we get an equation from?
Since they're connected, the displacement of x is equal to the displacement of y.
Yes. Someone over here had their hand. I want you to explain why he's right. Okay.
Is it because of the pulley?
Tell me more.
So earlier we said something along the lines of T equal T to the pulley. Is that why?
Okay, so it's not due to the pulley, although what you said is true. T equals T on the pulley. The pulley is not the reason. But you're getting closer. Okay, we'll go back here in the purple. Yes, because the rope is inextensible or cannot stretch. So therefore, if I scroll back up, if M1 moves any distance, M2 has to move in this correspondingly same distance as well, ignoring whether that's negative or positive for the coordinate. So we know that, or as we just said, since the rope is inextensible or inelastic, let's say inelastic, or no, inextensible, we'll stick with that. Then x must equal to y. What does that imply? Yep.
The magnitude of their accelerations will be the same.
Yes. What were you going to say? Okay. Which means that,
It's just one acceleration.
and what do I write? It's not, I'm not asking a hard question. You were probably overthinking it.
X double dot equals y double dot.
Exactly. X double dot is equal to y double dot. So then we can expand the right-hand side. We'll get m1 x double dot plus mu k m1 g equal to m2 g minus m2 x double dot. We can bring the m2 x double dot onto the left-hand side, and we'll take our terms of g onto the right-hand side. And so we'll get here m1 plus m2 times x double dot is equal to m2. That should be a quantity m2 minus mu k m1, all of that multiplied by g. Then we'll find that the acceleration x double dot, we're just going to divide by m1 plus m2, is equal to quantity m, I'm going to erase that fraction, m2 minus mu k m1, all of that multiplied by g, divided by m1 plus m2. And that is our solution. And if you go and plug in, and I'm going to use g equals 9.81 meters per second squared. If you go and plug in, you'll find that x double dot is equal to 3.08 meters per second squared. All right, any questions on this?
Why is x not equal to negative 1?
So, if you give me a moment, I'll just let people catch up and I'll answer that. So the question is, why is x not equal to negative y? The reason is, well, y is pointing down.
Right.
So
But wouldn't it, since it's pointing in the negative j-hat direction?
if that involves the position vector, not the displacement of the vector, of the mass. So y of t is the displacement of the second mass, or the change in its position, is what we say. But it's not a vector quantity, it's a scalar quantity. Now, we could have decided to put y of t upward, so it would have a positive j component. In that case, x would equal minus y, or y would equal minus x. Yeah, but because I strategically chose to put y pointing down, we end up not having that negative sign there. And then it shows up in the position vector instead. Other questions? Okay.